Oh, everybody's starting to come in. Okay, let's dive in. Hello, explorers. I see a very young explorer that's joining us today, which I'm very happy to see. Welcome to Dispatches from the Field, a new initiative from the Explorers Club designed to better bring our global community together on this virtual online platform. So we don't have to travel. Makes it easy. For those of you that are new to joining us, let me tell you a little bit about what to expect. This is an opportunity for us to be able to highlight the incredible work of our membership. We're going to start off with a roughly 10-minute featured talk, and then we will split up into what we call campfire sessions, which are small breakout groups really designed to allow us the space to connect, meet, tell stories, ask questions of the speaker, and get into all of the adventurous stuff that we always end up getting into. So, without further ado, for those of us that are sweltering in summer heat, let's take a cooling trip to the Canadian high Arctic. Please join me in welcoming Dr. Alison Criscitiello, ice core scientist, high altitude mountaineer, and a true explorer in every sense of the word. Alison is the director of the Canadian Ice Core Lab at the University of Alberta, where she studies the history of climate and sea ice in some of the most remote and extreme environments on Earth. Her research has taken her to Antarctica, Alaska, and the Canadian High Arctic, where she drills deep into ancient ice to uncover the environmental past, often while living in a month for tents, or living for months in a tent. She's also the co-founder of Girls on Ice Canada, a mentor to the next generation of scientists and climbers, and holds the first ever PhD in glaciology from MIT, a recipient of numerous alpine climbing awards and the Queen Elizabeth II Platinum Jubilee Medal, and of course, an EC50 awardee of the Explorers Club. Alison is a force. Please give a warm welcome to Dr. Alison Criscitiello.
Oh my goodness. I think I'm blushing. Thank you. Thank you so much. I'm going to share my screen so I can show some photos to you. So give me 1 second while I share. All right. Okay, well, thank you again for that blush-worthy intro. It's such a pleasure to be with you today and connect with folks who maybe I wouldn't get to meet in person anytime soon. I'm going to share with you what I just came back from. I spent 60 days drilling the deepest ice core in the Americas in April and May of this year on a little island in the Arctic Ocean at almost exactly 80 degrees north. And so that's what I thought I'd talk to you about today. Again, my name's Dr. Alison Criscitiello, and I live here in Edmonton in Northern Canada. I direct Canada's National Ice Core Lab, and I'm an assistant professor at University of Alberta. Just one, oh, can you see me? Just one very quick slide here first on why we drill these things. And this is a very brief overview, but I can't skip it. Why do we drill ice cores in the first place before I tell you why we drilled this one? They preserve the chemistry of the environment over time. And as snow falls and it gets compacted and buried, you get this time series going back in time as you go down. And it's a preservation of all sorts of different climate signals and of atmospheric chemistry as well. And each chemical species that we can look at in these climate archives can tell us something different about the past. I list 4 here of literally dozens and dozens that we look at. These are 4 that we typically look at in all ice cores these days, at least I do. But just to give you a quick flavor, we reconstruct temperature using stable isotopes in ice. We can reconstruct things that people care a lot about, especially right now, like wildfire frequency and intensity in the past to help us predict future wildfire behavior. And something else I'll talk about that we're really interested in the Canadian High Arctic is anthropogenic pollution. So we can also look at all sorts of environmental contaminants that travel atmospherically far from where the source was all the way to the most remote parts of our planet and get deposited in snow as well. And then sort of my niche area of original expertise was in using land-based ice cores like this one to look at changes in the ocean and sea ice in the past. So we look at different things that come out of the ocean, but also get atmospherically transported up onto land-based ice. So this is just a tiny snippet of what ice cores can tell us, but we kind of, in general, it's sort of a look backwards to help us understand what's to come in terms of future climate. Very quickly, these bright stars here are showing you locations that I've drilled some ice cores in the past decade. And this is a terrible map projection for pointing this out, but they all sort of hug the Baffin Bay, Greenland side of the Canadian Arctic archipelago. Axel Heiberg Island, where I'm taking you today, again, the projection doesn't show it, but it's much farther west and in the archipelago. And we've always believed that this is a location that would preserve a more Arctic Ocean signal and tell us something new about Arctic climate that these sort of more eastern Baffin Bay locations would be able to tell us. And another, I mean, it's sort of a not exciting reason for this, but where these stars are from the previous cores, part of the reason for those locations, there was science driving why they are where they are, but part of the reason they're there is because of logistical constraints working this far north. Resolute, which is written in blue there, is our logistical jumping off point for work in the Canadian high Arctic. And it's shockingly a lot easier to work where those stars are when you base your small fixed wing planes out of Resolute and all your gear staging than where Axel Heiberg is at 80 degrees north, or the ice cap on that island. So that's just a quick map. Now, here's what one of the outlet glaciers off the edge of the ice cap looks like, and this was from the site selection year prior to us doing the drilling. But one other reason that we went to Axel Heiberg to drill this year is because it's really has a very deep ice cap for a small island ice cap. We knew from doing radar the year before, it's about 600 meters thick, which is really exceptional for these small islands, with an estimated 10 to 20,000 year record in those 600-ish meters of ice. So a really long-term climate record that we expect to get out of here. And another sad but important point is that even at 80 degrees north in the height of summer, there is summer melt. So sort of this became a location of urgency, I would say, in terms of drilling, because the longer that we wait to drill locations like this, the more of the recent years of climate history we lose from melt. And I kind of mentioned this before, that we expect this location to contain a really nice long-term temperature, but also Arctic Ocean, Arctic sea ice record, to understand how continued warming may impact all sorts of communities and people, but specifically we hope to show impact that this warming may have on coastal Nunavut communities. And I'll say lastly, this project had 3 science goals. The first one was, of course, to drill this surface to bedrock ice core to get a full climate history from this location. The second one was to drill 4 what ended up being 70-meter cores in addition with a second drilling system. And the reason for those was to look at environmental contaminants. So we need a lot of sample to measure specific environmental contaminants that we care about that travel atmospherically to the far north and will have downstream impacts as they melt out of snowpack. And then the third scientific goal was doing what we call firn air pumping, where we actually suck the air out of the borehole after we drill the core. And we did this on one of the 70-meter cores. And this lets us look at all sorts of different components of the atmospheric chemistry in the past. There was also other surface sampling looking at methane budget and all sorts of other things. So there was a lot going on for these 2 months. I thought I'd show you quickly what it looks like when we fly into a small island ice cap like this in the Canadian high Arctic. We had to groom a runway, which is what you're looking at. I'm flying in on a Twin Otter in this shot, but we had to use Baslers because they have 3 times the payload. And this particular project was quite heavy when we had 15,000 pounds of ice come out. So you see that it looks like a runway. So we had a hasty team go in first with a small groomer on a Twin Otter, groom that runway, and then bring the rest of our team in. And then I just thought I'd walk you through really quickly what kind of what this sort of work looks like and entails. So with the deep drilling, we used a drill. It's a Danish drill called a Hanstausen, a big tipping tower drill. And we have to set up some sort of floorless tent system to be able to work in the horrendous storms that hit islands like this. We would lose probably half of our work days if we didn't. This is a new style tent. I think is pretty cool and had a huge impact on our work and our productivity in a good way. We usually use rigid structure weather havens, kind of military style historically, but our Danish colleagues who are ingenious worked with a company to get this thing. It's all the dark, what looks like it's rigid. It's not. It's a high pressure stanchions, really. So this tent is standing up because of high pressure structures, and it went up in about half the time that our old weather havens do. So this is something I think we'll use in ice core drilling and probably other sorts of climate research moving forward. And you can just see us setting it up there. And then on the right-hand side, when we drill these sort of intermediate kinds of depths, several hundred meters, we build a room. So we fly in a bunch of lumber and we decide, what our priorities are, what we're going to do in terms of analysis in the field, that kind of thing, and packaging and measuring and weighing ice. And we build a room around that. So you can see on the right-hand side, we're starting to build the railing system around the big incline trench that the drill will swing into. And then on the right-hand side, we ended up building basically a wood shop. That's what it looks like, but a little core processing area.
Allie, where are we?
And here, sorry that I always listen to music when I'm drilling, but here's 1 minute of a run coming up where I'm talking to Taylor Godber, a teammate of mine.
Allie, where are we?
Where are we?
Yeah.
We're in the deep drill tent on Axel Heiberg Island.
And what is going on down here?
Well, there's a very deep incline trench that the big 10,000 drill is going into. We're at 475 meters depth right now. And it's drilling like in 2-meter sections. 1.1 meters into a 2-meter run. Yeah.
I hear that's a scientific record.
I mean, every meter we drill it. Yeah.
Every meter now is
The deepest ice core ever drilled in Canada.
That's so cool. And then over here, we have one of the cores. Ladies and
I just thought I'd show you that. It's I mean, showing drilling can be a little bit boring, especially when you're at 475 meters where a core comes up every couple of hours. But that's what it looks like. And we build a whole flooring system that this black, it's called geoblock. So we build this whole room. Also because, probably worth mentioning, we have to use drill fluid once we get below a certain depth where the pressure is high enough that when we pluck that meter or 2 meters in this case of ice out from its happy home, it wants to shatter because it's under such high pressure that it goes instantly to atmosphere and shatters. When we start seeing really bad core quality like that, which will make our analysis really hard, we pour this kind of terrible drill fluid down the hole. We use something called Estisol 140. And then it's great for drill fluid. It doesn't impact our analyses. It makes it harder to work, and it eats almost every material, including your boots and the geoblock and everything. So you can tell on the left here, I'm showing kind of when we were near the surface, that was probably at, 20 or 30 meters. It looks like snow that's sticking out of the end of the barrel. And you can also tell that the floor and our boots are still, everything looks clean a month later, and everything's black from all the Estisol eating everything. In the middle, you can see we've transitioned at that point. That was quite deep to beautiful, pretty clear ice that has obviously low gas content. It looks pretty clear, right? And then on the right-hand side, that was very near the bottom, right before that beautiful clear ice suddenly turned murky, and we knew we were near bedrock. For me, as an ice core scientist, this is something that happens a couple times in my lifetime, where you drill a deep core and you hit bedrock. So it's really exciting to use this thing we call Arnold, which is the kind of a bedrock smasher. It's used to determine, or I guess confirm, that we've hit bedrock. So in the photo on the right, you can see the drill barrel, the normal drill barrel with Arnold on the right. And we use the normal apparatus, but we pull the drill barrel off it. We stick this pointy thing on the end and we confirm that we've hit bedrock. And we spend days doing that to make certain. It's shockingly hard to determine that you've actually hit bedrock. And in the middle, this was one of the last meters of ice where you can see that we were pulling up huge pieces of rock. And the drilling gets very slow. It's grinding its way through rock as you try to actually hit the bottom. Yeah, and then just one quick slide on, I said that this was also, I would say, scientifically as important, these shallow cores that we drilled to get more material over sort of the Anthropocene. And this is the Canadian eclipse drill. If others know my other recent work, this is the drill that was on the summit of Mount Logan. It's a lightweight, modular, amazing drill that is in principle very similar to the Hans-Tausen, but just smaller. It can't go quite as deep. So you can see it on the left-hand side in its sort of drilling position, and then I'm swinging it there upright in the middle. And you can see it in its ice retrieving position on the right. So we did successfully drill these 4 70-meter cores in addition. My last slide, there are a lot of reasons why this matters, but as an additional and kind of broad step back point, I just wanted to highlight that even though these places are unbelievably beautiful and pristine and just seemingly untouched, both the Canadian high Arctic, the high Arctic in general, as well as the highest mountain ranges in our world, they seem like these places that would be sheltered and sort of persist the longest and be untouched by warming, and this is not the case. These places are, some of them, in fact, the most impacted by climate change because of elevation-dependent warming, a process by which high elevation locations are actually receiving more heat. So that's just a bit of a broad step back as to why some of this work is so critical in locations like Axel Heiberg Island. This is an enormous project that I just tried to share in 10 minutes with a lot of people, years of logistical planning, and I am one tiny piece of an enormous international team. It's just me, the mouthpiece today, but this takes a lot of incredible scientists and countries to pull off. So thank you so much.
Ali, thank you. Thank you so much for sharing this incredible project. I know that we're literally just at the tip of what it is that you could discuss. I instinctively found myself leaning over during that video to look down into where the cord was. And as Tom said in the chat, learning about this is basically anything but boring. But we do have a few quick questions that I just want to highlight. Which months do you normally conduct drilling during?
That's a great question. We normally go kind of mid-May to mid-June, and I really like that question. This is something that has changed because of changes in summer melt and this extended kind of melt season, which makes it impossible for twin otters like the one in this picture to land and remove us at the end of the season. So for the cores that I had shown with those bright stars, those I all drilled kind of month of May. For this project, we went in when it was, this is even me saying unbearably cold, like low -40s. And we only that was April 1st. We only did that for this project because we wanted to do this in 1 year, and this is normally a depth that we would drill in 2 seasons. But yeah, so this is not a good example. We pushed it on both ends. We pushed it on the front end going in the first week of April, where it was very difficult to set up and work. And then by the middle of the season, end of April, beginning of May, it was perfect. And by the end of May, early June, when we were coming out, it sounds weird, but it was too warm. So our season for working without really pushing it like we did with this is shortening. Yeah, early May is kind of the right, like in the middle sweet spot where it's kind of -20s and easy to work, not too cold.
That kind of dovetails perfectly into Rachel's question of how do you transport the ice cores back safely so that you've got the structure, you've got the appropriate temperature, you're not losing any information, especially given what you just said.
Yeah, thank you for asking all the slides I had to cut. Um, I it also seems kind of silly, but it's an important part of the job is figuring out these kind of cold chain logistics. This was a complicated one because we couldn't work out of Resolute. I kind of mentioned that at the beginning. Um, we worked for my first time, we used as a hub for all of our equipment and the ice coming out Eureka Weather Station, which is on Ellesmere Island, but it's a short flight. It's like 30-minute flight. So when we went in, we built a freezer in Eureka and we built a freezer in Yellowknife. These really cool German modular freezers called Wiesmann's. I don't know. This is also Danish ingenuity. So we had flown those to Yellowknife and Eureka and built them there. So once we had full Twin Otter loads or Bassler loads of ice on the surface on the ice cap ready to fly out, one of the small fixed wing planes came in and flew them cold deck, so on the frozen plane to the staged freezer in Eureka. And yeah, it was it was 15,000 pounds on about of ice total. When we had half of that in the freezer in Eureka, it then got flown on a private cold deck charter, Eureka to Yellowknife, where it's then sat in the freezer that we built there. So we did that whole thing twice. We did half of the ice, and then at the end of the season, we did the other half. And then it got on a freezer truck and traveled from Yellowknife all the way back here to my lab in Edmonton. And much like Logan, the last deeper drilling project of mine, it almost beat me back here. I arrived within days of the ice, the truck reaching Edmonton. So that's kind of what it looked like.
Incredible, incredible. Tim, I know you've got a great question too. I think maybe at this point, we'll split up into the campfire sessions, and I'm sure other people also have questions. So for all of you that have joined us, hang tight 1 second. We're going to be shuffled into groups. And Tim, I'd like to know the answer to your question too on that one. Allie, thank you so much. We look forward to
Yeah.
meeting you in the campfire sessions.